All right, let's look at the third way to handle concurrency in a server, which is to use threads. Well, thread-based server is like a process-based server, but it uses threads instead of processes. Well, I haven't exactly defined anything by saying that. So let's take a little bit of a look at what processes and threads are. What we saw about processes in some previous chapters, a process is has memory associated with it, and it has a context associated with it. That context including things like registers. Now, really, our processor only has one set of registers, but from the processor's point of view, it has its own, because every time we have a context switch, every time the operating system switches from one process to another, or from one process to the kernel, the registers are saved, the saved register of the process we're switching to are loaded, and everything is transparent to the process for the most part. Each process will have its own stack pointer, its own program counter, that is the instruction pointer, so each will be running its own code. And the memory belonging to that process also belongs to that process. Different processes have their own memory. There might be some sharing there, for example, in shared libraries, or when we call fork, there is a form of sharing called copy on write. But at least writable things are definitely not shared once we've written to them. So uh, that gives us a view from a programmer's point of view, someone writing code that's going to run in a process. So someone writing code other than a kernel programmer can really act as though we have the entire machine to ourselves. We're given a virtualized view of part of the machine, uh, but it looks like we have the entire thing. Well, let's kind of separate that out a little bit. Let's call the process, instead of just having this context, which has the things inside the process itself, but also some things in the kernel, like the virtual memory structures, the memory mappings that refer to this memory layout, the file descriptor table, and so on. Let's separate those out. And then we'll say the thread is the context of the process within the process, the set of registers, the stack pointer, the program counter, and so on, as well as a stack. So we've taken the stack from over here and kind of moved it into here. And well, the reason we do that is if we had uh, multiple process contexts, multiple things running at the same time, each calling their own functions, they really need to have their own stacks so they don't step on each other's toes. And then we have all the other memory stuff, the shared libraries, the heap, the stuff that we got from Mallet, for example, global variables, code. And we'll also, over on this side, put the kernel context. So the virtual memory structures, the things that are mapping these virtual memory addresses to physical memory, the file descriptors, and so on. And then when we do that, it's possible for us to have multiple threads, so multiple virtual CPUs or threads of execution, multiple things running at the same time, all using the same code, the same data, the same kernel context. Not just shared copy on write the way it is with fork, where it might be shared, but the moment we try to write to it, we get our own copy, but really, really shared. When we write to it, that write is reflected in all of the other threads running within the same process. So we just make multiple of these. Each has its own stack, each has its own set of registers, but they're all running code in the same piece of memory. They might not be running the same code. They probably won't be. One thread might be handling one function, one thread might be handling another function, but each of these threads is sharing all of the functions there. They might not be calling them at the same time, but they can call them at different times or at the same time if they want. So each thread has its own logical control flow. From each thread's point of view, it's executing one instruction and then another and then another. Each thread has its own stack. That is, each thread has its own set of local variables, so that if they're calling different functions or calling the same function, that doesn't those local variables don't step on each other's toes. But the threads share the same everything else. And notice that although these stacks are separate, they are still in the same memory space. They really are somewhere over here. It's just we've made multiple stacks. So a thread stack isn't actually protected from the other threads. We are running within the same process. Everything has access to all of the same memory. The threads all share their process ID, but they each have a separate thread ID, which is basically like a process ID, except you can have multiple thread IDs that belong to the same process. Now, as far as the programming model, processes, if you remember, form a hierarchy. Each process has a parent process, and we could draw a tree out of that. So every time we call fork, that means we're branching in this tree. So maybe process 0, maybe that's the init process, calls process 1, which handles a login. A login comes in, or which handles logins. A login comes in and it creates a shell process. Another login, it creates another shell process, and so on. And then this shell calls some function or some other program, and that program forks to call some other program, and so on. Well, in a thread, within a process, all the threads are considered peers. No thread has another thread as its parent. No thread has privilege over any of the other ones. They're all just things running within that process, all sharing the same stuff. And again, going back to the definition of concurrency, two things are concurrent if their flows of execution overlap in time. Those could be concurrent processes, with process A doing some stuff. We get a context switch to process B, which does some stuff, and so on. But they could also be threads within a process. There does have to be some kind of context switch when we switch from executing one thread to another, because all of this thread-specific stuff, the registers, the condition codes, the stack pointer, and so the instruction pointer, and so on, all have to be switched. But we don't have to change the virtual memory tables. We don't necessarily even have to have the kernel do anything, although typically it is involved in the process. And as with processes, if we have just a single core processor, we don't actually have things running at the same time. Our threads are concurrent. Their logical control flows overlap in time, but they're not parallel. They're not actually running at the same time. We're just switching back and forth between them quickly, time slicing. If we have a multi-core processor, though, we can actually have true parallelism. We can have, within one process, two threads of execution running at the same time, which means that a single process could use more than 100% of a CPU, because the different threads could be running on different CPUs, different cores. So there are lots of similarities between threads and processes, and some differences. So threads and processes each have their own logical control flow. Each is executing its own set of instructions. They can run concurrently with other things. They can even run in parallel with other things if we have different cores, actually at the same time, rather than just overlapping in duration. There do have to be context switches to get from one thread to another or one process to another, but there are some differences. They share all of their code and data, threads do, other than the stack. But even that stack, again, isn't necessarily protected from the other processes. It's just they have their own stack, or the other threads, they have their own stack, and by convention and not doing things that you shouldn't be doing, try not to mess with one another. Threads are also cheaper than processes because creating a process involves doing all of that copy on write stuff in at least all of the writable virtual memory. We have to update our virtual memory tables. The parent and the child will maybe be pointing at the same physical page, but the moment something happens, the moment one of them writes, we have to make a copy of it. But even if we never made that copy, just setting it up takes some time. So because of that, handling a process versus handling a thread, handling the process is a little slower on Linux, and these numbers are as of several years ago. So it might be a little bit different now, but probably only in that both of these numbers have changed in the same way. But on Linux, creating a process with fork and then reaping it with wait takes a total of about 20,000 clock cycles, assuming there aren't things happening that require us to wait for disk, for example. Doing the same thing with a thread can take more like half that time, about 10,000 clock cycles, potentially even less. So to create a thread and then to reap the thread, to wait for it to finish. So the way we handle threads in Unix is with the POSIX threads library, pthreads. So this is a standard library that's available on most Unix systems these days. That gives us a set of functions that allow us to create threads, reap threads, figure out our thread ID, terminate threads, a lot of the same things we do with processes. We also have some things about handling access to shared variables, which we'll talk about a lot more when we get to synchronization in lecture 18. All right, by the way, what is this POSIX here? You may have seen it once or twice before, particularly if you were paying close attention in man pages. You would see that some functions like wait PID refers to POSIX. Under conforming to, it says conforming to System 5, SVR4, System 5 Release 4, which was AT&T's version of Unix back in the 80s. 4.3 BSD, the Berkeley version of Unix back in the 80s. And POSIX 0.1-2001. POSIX is a standard for operating systems. It basically standardizes the Unix API. It's an international standard promulgated by it's actually shared between the ISO, the International Organization for Standardization, and and a consortium of Unix vendors. But this provides us a standard so that if someone wants to say, I'm POSIX compliant, they can implement these functions, get certified, and do that. And most Unix systems, well, I shouldn't say most Unix systems are POSIX compliant. Linux tries to follow POSIX, but most distributions, most versions of Linux haven't actually been submitted for certification. They can't say that they're POSIX compliant, but in practice they probably are. Mac OS is POSIX compliant. Windows, in fact, has a POSIX subsystem. The Windows subsystem for Unix, and more recently, the Windows subsystem for Linux. The Windows subsystem for Unix has even been certified as POSIX compliant. So, the POSIX here really means this is a standard. Um, what does POSIX stand for? It's Portable Operating System. IX, some people say it stands for interface. Really, it's just the last two words of Unix. They took Unix, which is a trademark at the time belonging to AT&T, but since passed around among multiple companies. Um, so they couldn't call the standard Unix, so they picked this. POSIX was actually suggested, or the name POSIX was suggested by uh, Richard M. Stallman, who is maybe more famous as the founder of the GNU project. So GCC, Bash, all of the C library and Linux all exist because of the GNU project, and he was its founder. Linux actually came around significantly later than the GNU project. The GNU project had most of what you need for a Unix except for a working kernel. Linux came along, implemented a kernel. GNU has its own kernel now as well called the Herd, but you've never heard of that because Linux ended up taking most of what might have become its market share. All right, so let's take a look at a simple threaded program. Which I actually don't have over here in the Lecture 17 code, so we'll take a look at it in the slides. This is a program that creates a thread, waits for that thread to finish, so that's like calling fork and wait, and then the thread does its thing. So we have a few library functions. These are the capitalized versions, so they come from the CSAPP library and do error checking and so on. The system version would be called lowercase p thread create. This creates a new thread. It needs to return a thread ID to us. So we'll pass in a pointer to a thread ID as an out parameter. It takes a oh, sorry, these pointers are actually going to the wrong place. It takes a set of thread attributes. Usually we pass in null there. We pass in a pointer to the function that we want to be called when we call that thread. We can also pass arguments to the function, but the arguments are just a void star, so just a pointer. And not only a pointer, but a pointer to unspecified memory. And then in the thread function, we take that void pointer. We could do things with it. For example, cast it to whatever type we actually wanted as argument and dereference it, assuming we set it up that way in the thread that created us. And then we return whatever we return from this function, which again is a void pointer. We'll eventually find out when we call pthread, or another thread will find out when it calls pthread join. Pthread join reaps a thread. We give it a thread ID. We give it a pointer to a pointer. The pointer that is pointed to will be overwritten with whatever the return value from the thread's process is. So this waits for that thread to finish, gives us its return value. So when this runs, main, so I say main thread, but it's not that it's privileged, it's the one that happened to be there when the program started, calls pthread create, which will return immediately, or very quickly. Pthread create calls, main then calls pthread join, which will just wait for the other thread. Notice I call it a peer thread, not a client, or not a child, because they are considered peers. Neither one of them has any particular influence over the other more than in the other direction. That thread, which was again implemented by this function, will do its printf, return null. That makes the thread terminate. When that happens, pthread join will return, and we will get the return value here. Eventually, our main thread we'll call exit, or some thread we'll call exit. When exit happens, that terminates all the threads. So it does exit the entire process. All right, so what about that echo server then? Let's take a look at echo server T. And we can see here that the loop actually looks pretty similar to what we had in the process server, with a few differences. We don't have to set up a signal handler because we're not going to have any child processes terminating. We're not going to get a sig child. We don't have to close things because the parent or the main thread and the peer thread here are in fact sharing their file descriptor table that belongs to the process. These two threads are part of the same process. So only one listening socket and one connected socket for each time we called accept will exist. Rather than having one copy of those in each of two different processes. Rather than calling fork and checking the return value with an if, we call pthread create. We pass in this thread. This thread does its thing. You'll notice it calls echo, calls close. So a few extra things we had to do for that connected file descriptor. So this is something that accept returned to us in the main thread, but we do need to pass it to the peer thread that's going to handle that connection. So we get that with malloc rather than just passing an integer. We'll see why a little bit later. Well, if you do remember, we have to pass the argument as a void pointer. Malloc happens to give us a void pointer, but there's a bit more to it than that. There's a reason we couldn't just pass a pointer to the connected file descriptor that accept returns. So, or to a local variable that we assign from accept. So we create this thing that's off in the heap. We call accept. We store it at that memory location pointed to by this pointer that we just malloced. In the thread, well, we got that as a void star, so we have to cast it, convert it to an int star. Of course, normally that's not safe to do unless we know it's pointing to an integer, but here we do because of how the parent or how the main thread was programmed. We dereference it. That takes that integer pointer, gives us the integer it points at, which was the connected file descriptor, and now we can call. We can do our stuff. We are doing a couple of things here, though. We're calling pthread detach. So we'll see a little bit more about that in a minute, but basically this says that this thread, if it exits, don't keep it around waiting for someone to join to it, waiting for someone to reap it. So with processes, we always have to reap them, or we'll end up with things in we'll end up with a memory leak, at least at the operating system level. But with threads, if we do pthread detach, we're saying I don't need to be reaped or automatically reap me. Don't require someone to do that. Don't require someone to call pthread join. We also have to free that pointer. Well, remember, it was allocated with malloc inside the loop. So every time we get that pointer, it has to, or every time we malloc that, we have to free it eventually, or again, we'll have a memory leak. And we're freeing it here in the thread that's handling it. So the reason we do it there is we can be guaranteed that we've already read the value that we need, the connected file descriptor that was number that was being pointed to before we free it. If we were to free it up here in the main thread, that might happen too early. We would have a race condition. And someone has to close the connected file descriptor. That should be the thread that's actually handling it, because it knows when echo is finished. We didn't have to do that twice because there's only one file descriptor here, not two file descriptors referring to the same open file. And it is important that we do that. Otherwise, we have not just a memory leak, but a file descriptor leak, and we have connections that are only half closed. The client has closed its side, but our server has not. So both operating systems have to maintain that connection in their table in case something exceptional happens. All right, so this is similar to the process-based execution model we saw before. There's a main thread. There's a thread handling each client. Those threads are all peers, though, running within the same process. They share all of their process state except for their thread ID, and they each do have their own separate stack. So they have separate local variables. All right, so in order to have a thread-based server, we need to run in detached mode. So what that means, and I mentioned it when we were looking at that pthread detach call, every thread is either joinable, meaning someone can call join on this thread to get its return value, or detached, meaning no one is going to join to us. No one can reap us. In fact, no other thread can kill us or terminate us, other than perhaps by calling exit. So a detached thread can't be reaped or killed by other threads, but the advantage of that is that its resources will be automatically reaped when it's terminated. Now, the problem here is that those resources include the return value. So if we need to know what a thread returned, it has to be joinable. Calling pthread join is the only way we can find its return value. By default, all threads are joinable, but you can make yourself detached by using pthread detach. It actually takes an argument, which is the thread ID, to detach. You can detach another thread, but usually we would do that in the thread itself. So we would usually use pthread itself, which is kind of like get PID. Instead of returning a process ID, it returns our own thread ID. We have to be careful to avoid unintended sharing. So I mentioned here it's important that we do this malloc. If we didn't, if instead we had either a local variable or, for that matter, just a global variable, well, in mains thread, there is one copy of this variable. Every time we go through the loop, we're going to, from the C point of view, have a different variable. Really, it just means that same memory location is most likely being reused to handle the next connected file descriptor. Well, what happens if we did this and we passed in the address of our local variable here to the other thread? Well, our other thread would get a pointer that points to that file descriptor, fine. But while that other thread is starting up, the main thread might keep going, depending on how many cores we have and how things get scheduled exactly, and overwrite that with another. And now, when our thread reads that connected file descriptor, it's going to read the wrong value. It's going to read one that belonged to, that should have been handled by a different thread. And in fact, that original one that we wanted might have been overwritten already. And if that happens, it's lost. We don't know about that file descriptor number anymore because it's not being stored anywhere. So we want to make sure that that we don't share things when we don't want to, and in particular, that connected file descriptor number shouldn't be shared among all the threads. Each one needs its own. Meaning we have to use something like malloc, so that every time we go through the loop, we're storing our file descriptor in a different memory location. And if we are using threads and we're calling functions from those threads, and of course we usually are, all the functions we call have to be thread safe. We'll talk about that in lecture 18. So thread-based designs make it really easy to share things. So we could have all of our threads logged to the same log file, or even the same in-memory data structure. We could have them share the same database connection. We could have them all share a cache of some kind. Threads are also more efficient than processes, both in terms of startup time, but also in memory overhead, because almost everything is shared. But having that sharing is a problem, because if we share things that we didn't intend to share, and it's really easy to do. If I had passed a pointer to a local variable in here to pthread create, I would have unintended sharing. And that can cause real problems. It's very, very hard to write a program that does that correctly. Chapter 18 or lecture 18 on synchronization, we'll talk about some of the ways to do that, but we'll see even there, it's something that we have to be very careful about doing. It takes a lot of mental bandwidth to reason about that. And the problem with these concurrency bugs, things like race conditions or deadlocks, the thing that makes them so hard to deal with after we've written our code, when we're trying to figure out what's going wrong or is it going to go right, is it's very hard to detect by testing, because chances are most of the time the peer thread here would have managed to read that pointer or would have managed to read that value before it got overwritten again. And if that's the case, everything will apparently work. But one time out of 10, or one time out of 100, or one time out of 1,000, or one time out of 1,000,000, it won't work. And well, what's even worse than a bug that happens all the time? One that only happens some of the time. If you can't just go into a debugger and reproduce it, it becomes a lot harder to figure out what's going on. So again, we'll see more about that in future lectures. So again, as a summary, the different approaches we have to concurrency in a server are process-based concurrency, which makes it hard to share resources, but the flip side of that is we're not going to have any unintended sharing, at least unless we work for it. There is a fairly high overhead in handling a new client coming in, because we do have to create a new process. Event-based concurrency is kind of tedious and low level to implement, but the programmer has total control over what's going on. We can decide what order we handle things in. There's very low overhead. We don't have to create new processes or new threads. We just have to maintain and maybe an array of our connected file descriptors, for example. It's hard to do fine-grained concurrency. It's hard to have these multiple the handlers for multiple clients actually overlap in time, particularly if it takes some time to handle even a single client request. And it only works on one core at a time, unless we use a hybrid with one of the other methods. And then thread-based concurrency, it's very easy to share resources among the threads. The problem is it's maybe a little too easy. The overhead is medium. It's more overhead than event-based, but less than process-based, about half as much as process-based in common cases. As with processes, you don't have much control over the scheduling how the scheduling happens. You can't really say, I really want this particular thread to get priority over this other thread. And it's very difficult to debug, because if I do the same thing again, the order in which events happen is probably going to be different. And that might result, if I have a race condition, in different things happening. All right, so thanks for watching the videos on concurrency. In the next videos, I'll talk about synchronization, which is a way to try to avoid, mitigate, or handle some of these problems with thread-based and really, actually, sometimes even process-based programming. How can we be careful not to share resources in a way that causes deadlocks and um, race conditions. So anyway, I will see you in a future video. Thanks for watching.